Oh, and reminder while that starts. So your first homework's due tonight at 11:59 p.m. On WebAssign, and the other homework's already up. So don't get confused. The homework one's due tonight, and then the homework two has already appeared, but that's for this week. And pretty much, I'm not going to keep reminding you because honestly, I will forget to remind you. But it's just Tuesday to Tuesday. So every Tuesday, you'll have something due unless there's an exam that week. Well, I should be careful with that. Sometimes you'll still have one due right before an exam if the exam's on like Thursday or something. The only time that'll change is potentially around exams, and then one Tuesday there's that wellness day, and I can't have things due on wellness days, so I'll remind you when that one comes up, because then that one will we do probably just Wednesday. But anyway, so that's due tonight. If you have any questions, let me know. And yeah, so we're working on these propositional logic proofs, which use our rules off to the side here, our inference and our equivalence rules. So what we're going to do is we're going to do two more from scratch. Remember, when it comes to an exam or a quiz, you won't have them from scratch. You'll have them like this one that we started with the other day, where you just fill out the statements and the reasons. Also, if you haven't seen already, there's some extra practice for these up on Blackboard, and there's some videos. I walk through the actual problems, and then I do a bit of rambling about the stuff in general. So if you want extra practice, there's some up there as well. Anyway, moving on to this question. So given that Andy is hungry and the refrigerator is empty, then Andy is mad is a true statement. And also given that Andy is not mad and the refrigerator is empty, show that Andy is not hungry. So this one, we've actually technically already found the conclusion for in the truth table in the section prior to this. But now we're going to see how a proof table for this would be much shorter than that long, obnoxious truth table that we did. So remember, we essentially have three statements, and here we're gonna name them P, Q, and R instead. I think the other time I named them H, R, and M. But so essentially we're given that if Andy is hungry, then the refrigerator is empty. So we're given if Andy is hungry, so if P and the refrigerator is empty, so Q, then he is mad. So we have P and Q implies R. We also are given that he's not mad, so we have not R, and we're given that the refrigerator is empty, so we have Q. So that's essentially what we are given, and then what we're set to actually prove here is we want to take all of those givens, and we want to somehow imply that Andy is not hungry. So we want to show that he's not hungry, so we want to show not P. So if we're going to start doing this, remember the first thing you always write down is all the givens. So I'm going to write down the givens for the third time. So we write down all of our givens. And obviously, because there's not very much room, this is actually going to be a pretty short proof. But these are all given. So remember, you always state them as given, 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 given. And now here comes all the thunking we have to do. I should not use that word. So we look over at our rules, and remember there's kind of two approaches you can take to this. You can kind of do like a forwards approach where you just see what you have, try to see how you can manipulate it. Or what I like to do a lot is I like to try to work backwards. So I want to see where I want to end up, and I try to figure out the rules that will get me there. I want to try to do a forward proof on this one though. So let's look at what we have in all of our rules and see if we can figure out some things that we could get. So I'm going to come off to the side here, do a bunch of scratch work. Possible results. Sure. And by that I mean, what can we get from the rules that we have? Ooh, there it is. Lagged a little bit there. So we're looking at this and notice that we have not R and Q by themselves. And if we ever have two things directly by themselves, we could always plop them together. So if I just wanted to start randomly listing like almost everything I could get out of here, I could get not R and Q. That would be by conjunction, right? If you ever have just two things by themselves, you can always plop them together with an and. I could plop them together in the opposite direction as well, but to save myself some space, I'm not going to write that down. I have the P and Q implies R and not R. That's a setup for modus ponens. Sorry, modus tollens. So if I used modus tollens on this, I would get not P and Q. So that's a thing I could get. And now I'm starting to think if there's a different way I could go about this proof. That's not the one I did in the notes because that just made me think of something. What are we trying to get? We're trying to get that. Well, that's another way we could do it. I might do that way. Okay. But a couple other things just to make note of other things we could do here. The other thing is you do want to think of this P and Q as its own separate thing. Like you could manipulate that by itself. So if we wanted to, we could change this to just P by simplification. So we could also get that. We could also get just Q if we swapped it around. So that's cool. So that's a couple things that I could get. Is there anything else I could get? I think those are the three main things that we can really do that would be helpful. I mean, technically, if we wanted to use De Morgan's law on this P and Q, we could, but that doesn't really look like it's going to get us anywhere. So this first one doesn't really do anything for us because it doesn't help us get to anything in terms of just P. Like, sure, that gets us another statement, but it doesn't seem like it's going to help us at all. So one of these other two seems like it's going to be the better bet. And actually, either one would be fine. So I'm going to go with the way that I did it in my notes, and then I will show you a different way as well. So the way I did it in my notes is I used the simplification rule to just get P implies R. So notice I used the simplification on just that front piece, but since it already had an implies R to it, I had to keep the implies R. But this would be from simplification on line 1, where I just changed the P and Q to just a P. And now that I have P implies R and not R, I can use modus tollens. So now that I have just P implies R, I can use modus tollens to just get not P, which is what I need. So that would be modus tollens on 2 and 4. And then technically we're done. Because that's the proof. That's what we wanted to find. Really quickly, I'm gonna like try to squeeze it in here as like a second option. Maybe I should do this first. Boop. Let me, nope. Oh, come on, stop it. You swoosh that over there and then do a second option over here. So the other option is if you had actually recognized to use modus tollens. Oh, but then the reasons are gonna look stupid. Okay, let's undo that. I'm just gonna. So I should have left it. Anyway, I'm gonna do my thing. So where'd my thing go? Sorry. So if instead of using simplification, you recognize that modus tollens was essentially set up there for you, and you would have gotten not P and Q, that would have been modus tollens. I'm going to abbreviate because I'm running out of space. And then if you were to use De Morgan's law on that, you would get not P or not Q. Oh wait, no, that wouldn't work. Nope, never mind. That didn't work. But that was actually kind of nice because then you can see how sometimes you think it's going to work and then you realize it's not. So what I thought was going to happen is I thought that I could simplify that, but it was an or, not an and, so you can't simplify that, so never mind. So sometimes you try something and it doesn't work and you got to try something else. Anyway, questions, concerns on that question? So again, also you could kind of work backwards. So you could start to think to yourself, what would get you not P? And you might recognize that modus tollens looks like a good setup to get you not P. And then you could potentially see how to get yourself to P implies R by that simplification. So trying to look at it backwards can help as well. So this is an equivalent way to that really long truth table that we did last section. We came to the same conclusion. All right. So compare the truth table, which seems cleaner. The proof seems cleaner, but the proof can be more complicated. So I've kind of said this next bit a ton already, but sometimes you don't see the next step. So if that happens, if you're stuck and you can't see exactly what rules you can use on the things you have, work backwards. Start with what you want and try to figure out the rule that can get you there and see if you can get to that place. So say we want to prove the following thing. So we have three givens here. We have P implies R, and Q implies not R are our givens. And we want to try to somehow result in not Q. So let me come off to the side really quick and try to figure out some rules that could potentially get me there. Now, if you ever have more than one given, you definitely want to have modus ponens and modus tollens in the back of your head because those are very useful. They're used a ton when you have more than one given. And especially since one of these givens, is part of the implication, that's another big sign that a modus might be a potentially really good case. So while I jump over to the side, I'm going to completely forget my givens. I'm not going to care about what my givens are. I'm just going to care about what could get me the thing that I want. So if I look at modus ponens first, I could technically get a not Q out of modus ponens. You just need to be a little clever. So modus ponens could get me a not Q if I had a not Q in the back of an implies, and then I had anything I needed here. So those would just have to be the same thing, but they could be either P or R or some random other variable that somehow jumped in here, which wouldn't happen. And then the other way I could potentially get a not Q would be from modus tollens. Now modus tollens, we need to be a little careful here. So in modus tollens, the rule states a not P. And then there's a P in the implication. So we would have had a Q in the front of the implication. That's going to imply anything it needs to, and we'd need a not that thing. Now, notice this one's modus tollens is looking pretty nice because we do have Q implies something. So right now we have Q implies R, so we would need a not R. We don't have that so far. Oh, I'm sorry. We have Q implies not R. I'm sorry, I read that wrong. We have a Q implies not R, so we would need a not R or a positive R if you prefer. Or just regular R. And if we were to get those two things, then we would result in our not Q that we need. So that looks like a pretty good place to try to get to. So can we somehow produce, the only thing we're missing is a not R or a regular R. So is there any way that I can get an R? Well, the only other R I have is in the P implies R. Okay. Is there a way that I could take that out or get that from something? The answer is yes. If we look over at our rules, what could get us R? Well, something that pulls the thing from the end of an implies is modus ponens. So modus ponens, as long as you have the implication and the hypothesis of the implication, you can conclude the conclusion. So since we have P and P implies R by modus ponens, which I really wish I could highlight, but it's a different screen. By modus ponens, we can produce R. So modus ponens on 1 and 2. Now, when we're doing these proofs, when you're doing them formally, you have to be super formal and super precise in a way that almost seems stupid. So in my setup for modus tollens over here, I said that I either needed a not R or a positive R, if you will. So I have the quote unquote positive R. But to be actually precise, we would actually need to write it as not R. So the first thing we would actually need to do is take an extra step here to make this a not R by double negation. It's just how proofs go. You have to have that not in there to kind of say that you can actually use modus tollens. They need to see the not, because I don't know who they are, but the people who decided that this is a thing decided that you need to have that not in there.
It's big math.
Yeah. So now that we have Q implies not R, and we have the negation of not R, we can use modus tollens to produce not Q. So we can use modus tollens to produce not Q. That would be modus tollens on 3 and 5. Questions, concerns on that? Again, I know these take a ton of time to get used to and to get good at. Don't feel bad if you're like, how the heck is she? It takes time. I've been doing this too long. I know I seem like I'm 12, but.
So, Erin, when we come across this in our first exam, will we need to get every little tick correct, or if there's like 3 ticks that we need to fill in, like what reason for 3, 4, 5, and 6, and we give 2 of the 3 correct, do we get credit for those 2, or is that an entire question wrong?
Oh no, I do partial credit like it's my job. So yeah, no, it's something where like if the thing's worth 5 points and there's 5 blanks, then each blank is 1 point or something like that. So yeah, if you get part of them right, you'll get partial credit for that question. All right, any more questions about this type of topic as well? Because if not, we're moving on to 1-3, which is slightly different. Am I gonna need to keep these up? I don't think so. Especially not today. We'll probably need them all. I'm babbling to myself. I'm sorry. Okay. All right. Well, I will leave that there just in case I need it. But let's do this. And 1-3. I forget when this class ends. This class ends at 12:55. I'm trying to check. All right, so 12:50. Okay, yeah. All right, so section 3 is something called predicate logic. So we started with formal logic, then we did propositional logic, and now we're on to something called predicate logic. So in the first section, I told you that x is even would not be a statement because x is a free variable. So we were considering that not to be a statement because we don't know if it's true or false, because it could be anything because x is free. But in math, we often need to have phrases like that. So in this section, essentially what we're doing is we're going to extend our knowledge of formal logic to be able to deal, with unknown variables. So what happens is we have these new things called predicates. So a predicate is a declarative statement whose true-false value depends on one or more variables. So it's not a statement, it's predicate. So x is even would be a predicate, not a statement. So notation-wise, what we're going to use is, it's almost going to look like function notation. You know how f of x, g of x, h of x, it's going to look like that to denote predicates. And we're going to use that to be able to show the true falseness of that now statement. Like once you add a predicate on, it becomes a statement. So for example, say I would say something like, let p of x mean x is even, or let q of x, y, be that x is faster than y. So you can also have more than one variable. And so essentially we'll have this type of function notation to be able to write it really compactly. And then it'll tell us what it actually means. And once you tack on this, once you make it a predicate, it now has a true or false value. So say I said p of 7, which would mean that 7 is even. Well, that would be false, because if we're saying 7 is even, it's not. It's not a number. So even though x is even isn't a statement, and we couldn't determine the true-false value because we don't know what it is, once we now let x be equal to something, it's got a true-false value. So if instead we looked at Q leopard sloth, that would be saying that a leopard is faster than sloth. That's very good grammar, you know? Leopard is faster than sloth. Is a leopard faster than a sloth? Yeah, probably. So that would be true. Even though the x is faster than y, we didn't know it's true or false, but once we add in those kind of values for those variables, we can tell if it is. Whereas if you switch the order, so the order really matters because then it would change to sloth is faster than leopard, which is false. I would love to see a sloth move faster than a leopard. So you really want to be careful with these. The order really does matter. So whatever order you're given is the order that they go into the variables in the statement. Or I should be careful with the way I just phrased that. If for some strange reason, so I'm not saying these are equal or anything, but coming off of here really, really quick, and then I'm going to erase it so people don't get confused. If for some strange reason they wrote it like this, but it still said x is faster than y, then me saying that they go in the correct order is technically a lie. Just be careful, look at how the predicate format matches up with the actual statement and just put the things in the right spot. Usually it's given in, you know, the order that it's listed in the statement, but anyway. So the domain is the set of values that the variable can take. So it kind of works exactly like a function. Like the domain of a function is the things that you're allowed to plug into that function. The domain of these predicates are the things that you're allowed to plug into the predicate. And it doesn't have to be numbers. So I know like with functions, pretty much all of our domains are always functions. In the above, with the Q leopard sloth, the domain would be the set of all animals, for instance. Which is exactly what I say down here. So in the above, the P of X would have been a domain of all integers, and the Q of XY would have been a set of all animals. This is something that you pretty much have to be told. You can't really assume the domain. It has to be told to you, because if I was talking about P of X, what if I made, like, I don't know if that's the integers, if that's the real numbers, if it's whole numbers, if it's rational numbers. So I can't just assume one of them. It's something that you would have to be told. So just be aware of that. In the questions up here, it didn't really matter what the domain is. So sometimes the domain doesn't matter, so they won't tell you. But there are other questions where it really does matter, and then they'll have to tell you what the domain is. Anyway. So again, it works very similar to functions in math. What can you plug in? That's the domain. So we can actually also think of equations as declarative statements where the equal sign would actually be the verb. So if we consider the function x squared minus x minus 6 equals 0, we can actually call that essentially the predicate statement e of x. And then we can determine the truth statement of e of x depending on what that x value is. So say I had e of 4, well, that would mean that I'm plugging in a 4 everywhere I see an x into the function. I'll just put parentheses around them to be, and I'll put a question mark because I don't know if it's true or not yet. So if we plug in 4, we would get 16 minus 4 minus 6. What in God's name? Oh, right. So 16 minus, my notes freaked me out for a second, which would be 6, which is not 0. So since when I plug in 4 to this equation, I get 6, but I was comparing it to 0 because that was my statement. My statement was that thing equaled 0. This would be false, because when I plugged in 4, I didn't get 0. Whereas e of 3, we do the same thing, but with 3. Nope, 3 squared, not cubed. And we want to know if that would be equal to 0. We would have 9 minus 3 minus 6, so 9 minus 9 is 0. So that would be true. So we can also kind of use these in terms of just generic functions. We can have a function as the statement, if you will. And then depending on the value of the variable, it'll either be true or false.
In the long term or whatever, are we allowed to like just factor it? Because like all I did was factor and got x like was equal to 3 and 2, and so I knew 4 was false.
So yes, but you would have to also add on a little bit of explanation to that. So you would have to tack on, because this function is only equal to 0 at 3 and 2, 3 and what would it be, -2? Anyway, therefore this function is not 0 at 4 or something like that. Like something that tells them that you know why that factoring got you the answer. Does that make sense?
Yeah, okay. Thank you.
So I would say it's almost faster to just plug it in, but I mean, technically you could do it that way and just have to give them a little bit of an explanation. Questions, concerns so far before I scroll down? Okay. Next definition then. A quantifier describes whether the predicate is true for all elements of the domain or for some elements in the domain. So now we're going to be working with predicates that have these quantifiers attached to them, and the quantifier is going to tell us whether we whether we need to consider all things or just some things. So there's the universal quantifier, which looks like an upside down A, and this is going to be for all is usually how you'll read it, or sometimes people will say for every, and you'll see kind of how it's used in a second. And then there's the existential quantifier, which is like a backwards E, which means there exists, or sometimes people will just say there is a, just there is. Notation matters. I've never seen someone do this, but it's an upside down A, not a regular A. And it's a backwards E, not a regular E. How do you suggest we type those? That's a good question. So in Blackboard, if you were ever doing something like this on an exam or a quiz, it has a function editor that has the symbols in it. If you're just trying to type these on your keyboard, that's a good question. Is there like a little shortcutty way to write that? Let me search that real quick. That's not helpful. I mean, obviously you can find them in like most like Word and everything has the symbols, but then you gotta search for them and that's annoying. I can't find an easy way to do it without having to find the symbol somewhere and then like copy and paste it over. I'll look into that a little bit more. For now, for like if you're just trying to type these notes out on the PDF like we discovered we could do, then you can just write capital A and capital E for now and just remember in your brain that that's technically wrong. Oh, I could try to remember to do that. Yeah. Could you provide them on the quiz and we can just copy and paste them? I'll try to make sure I do that. I'm gonna write myself a sticky note. Because that's actually a good idea. Sticky note. Okay. So yeah, I'll try to make sure to remember to put those in like the instructions or something so you can try to copy paste them. For the sake of right now, if you need to, just do capital E and capital A and keep it in the back of your mind that that's wrong. So Those are our two quantifiers. So essentially, if we have the for all quantifier, that means that it has to be true or false for absolutely all of them. Or shall I say it has to hold for all of them. And whether or not it holds for all of them will tell us whether it's true or false. And then there just has to be one of them that it holds for. It could hold for more than one, but there has to be at least one. So a quantified statement is a predicate with a quantifier in front of it. So let's suppose that our domain that we're talking about is all animals. We're talking about all animals, and let's let P of X be the statement X can fly, and Q of X be the statement X has wings. So if I wanted to say for all X, Q of X implies P of X, what this is going to mean is, so I'm going to write it out in like the formal language, and then I'll write it in a bit more modern English. But if we were writing this out like formally, we would say for all X, for all animals X. So the for all, of course, comes from the upside down A. You always have to state the domain when you're doing these interpretation ones, which is why they need to tell you the domain. But you would say for all animals X, if, so Q of X would mean X has wings. So if X has wings, then X can fly. A bit more of a usual way to state this in modern English might be something like all animals with wings can fly. You know, if it has wings, it can fly, so all animals that have wings can fly. This is false. Like, I'm not saying that this is a true statement. So yeah, this is false because penguins, poor little penguins, can't fly. So this statement is false. So that's kind of what the quantifiers help do, is it helps to kind of restrict. Maybe I should be careful with the word restrict. Because it puts some type of context to the domain. We're talking about all animals, not just some animals. If I just said, if an animal has wings, then it can fly, it would depend on what the animal is. But since I'm saying that now it has to be over all animals, it turns into a false statement because penguins exist. So whenever there's a quantifier on a statement, it will always either be true or false. If it was just this predicate in the back, then it depends on what animal you're talking about. If a cardinal has wings, then a cardinal can fly is true. But if a penguin has wings, a penguin can fly is false. Anyway. So what if we wanted to say in symbols, so now we have the words and we want to put it in symbols, there are some animals that have wings and cannot fly. So essentially, yeah, ostriches too. I was once driving home one day to my parents when I lived at my parents' house, and an emu ran across my driveway because there was apparently an emu farm down the road. So that was cool. Anyway, random story of the day. Anyway, there are some animals that have wings and cannot fly. Our penguins penguins, ostriches. I like pushed penguins and ostriches together. I don't know what happened there. Anyway, so if we wanted to say this in symbols and predicates, there are some. So there exists some animal that has wings and cannot fly. Emus are a little scary. So there exists some animals that have wings but cannot fly. So this would be a case of a there exists. So there are some is essentially what tells us that there exists. So there exists some animal X such that it has wings, so Q of X, but it can't fly. And that would actually be an and, not P of X. So there exists an animal such that it has wings and it cannot fly. Now we should get there today. In a couple of minutes, I'll kind of note a very common, so notice that the for all was attached to an implies and this there exists came attached to an and. That's actually incredibly common. It's pretty much how it works. For all is going to be matched with implies, and there exists is going to be attached to an and we're going to talk about that a little bit more in a second, and it'll be written down and stuff like that. So I'll get back there in a second, but just to kind of preview where we're going. Is everyone okay with how I created those statements? So one in words and one in symbols. Okay. So as I already kind of mentioned, since the quantifiers change the variables that the variables of the predicate can take, the quantified statement is either true or false, but not both. So whenever you tack that quantifier on it, now it has to be either true or false. Then we have something called the scope. So the scope is the part of the formula for which the quantifier refers to. So it's essentially what lies in parentheses after the quantifier. So in the first one up here, the quantifier of the for all was the Q of x implies P of x, and the scope, I didn't say scope, did I? The scope of the for all, maybe I did, was Q of x implies P of x, and the scope of the there exists is the Q of x and not P of x. Now, you need to be really careful, because if you saw something like this, there exists P of x and Q of x, and then at the end, and R of x. The only thing that's in the scope of the there exists is the P of x and Q of x. That little tacked on the back and R of x is actually considered outside of the scope of that existential quantifier. Okay, so that's be careful when you're reading statements, and also if you're writing statements. If you're trying to write these quantified statements and you want that quantifier to go to that entire statement, make sure that entire statement is tacked in some parentheses to make sure it's in the entire scope. Okay, so translating between English and predicate logic can take some practice, like everything I've been saying. So take some practice. So consider the following predicates where the domain is the set of all mammals. Translate the given sentence into predicate logic. So we have B of x means that x is bear, f of x means that x is fuzzy. So if I wanted to put in symbols, all bears are fuzzy. Well, the word all should probably tip you off that it's probably going to be a for all statement. So all bears are fuzzy. So we would be starting with a for all x. Now, that x, as it stands right now, is all mammals. So this is starting out with for all mammals. So we're saying that all bears are fuzzy. So it needs to be if it's a bear, then it's fuzzy. So this would result in if it's a bear implies that it's fuzzy. Now, maybe I'll write this up here instead of kind of squeezing it in the next part, which I was going to. So this is kind of written out below, but to kind of explain why. For all x, I'm going to say matches with an implies. And here's kind of why. It's because we have to narrow it down. And by it, I mean the domain. We need to narrow the domain down. So essentially, if I had instead written for all x, bx, and fx. So say you thought, okay, well, what if it was supposed to be it's a bear and it's fuzzy? You might think that that would be a proper translation for this, but that would actually do a bit too much, because in that statement, this means everything, because it's a for all, has the property b of x. So if you were to phrase it like that, that's essentially, oh, it froze. There we go. That's essentially saying for all mammals, it is a bear and it is fuzzy. So now there's no other mammals that exist besides fuzzy bears. So that's why it kind of matches with the implies instead, because we kind of have to narrow it down to just bears. So for all x, all of the mammals, we're going to shove it down to just bears. And if it's a bear, then it has to be fuzzy. Whereas the opposite not direction. Anyway, the second one says some bears are fuzzy. So some bears, not all bears. So there exists at least one bear that is fuzzy. So this would be there exists. So there exists some mammal such that it's a bear and it's fuzzy. So this one does have the and. Specifically because, again, this one's not talking about all things then. It's just saying there exists a bear that is also fuzzy. So if you're curious as to why this doesn't go to implies, so this matches with an and, because we need existence, really. Because we need existence. And actually the there exists does not quite get it. So if you were wondering why we couldn't say there exists, if it's a bear, then it's fuzzy. Because it's an if it's a bear, that doesn't actually mean there needs to be a bear. So it's kind of like when we were talking about implies at first, and I kept going back to that one where if it's raining, then I'll drive you home, but if it's not raining, then who knows? That's kind of like what would happen here if you tried to do an implies here. It says there exists an animal such that if it's a bear, well, what if there are no bears? Then the statement doesn't really do anything, and we actually need there to be one bear. So it needs to be and because there actually needs to be that existence. So what do I want to say here? What I want to say is saying if b of x. And the thing is, which we can't assume is true. Which is why it has to be an and instead of an implies, because it might seem silly to say, but we can't, if it's an implies, we can't assume that there exists a bear. And we need there to exist a bear. So anyway, if that reasoning freaks you out too much, just try to remember in your head for all's matches with implies and maybe just forget about why and exists goes with there. Yeah, and all things that are fuzzy are not necessarily bears. Yeah. So this is saying that it has to have both things. There exists something such that it is a bear and it's fuzzy. So hold on a few seconds in case someone's taking that down still. And then essentially what's below is kind of what I've already been saying, just written out formally. In the above setups, we have these in the above examples, we have common setups. All blank are something, and there is a blank that is something. So again, for all is going to match with the implies, and p of x is going to match with and. So that's just saying what I've said a couple times over, just formally writing it down. So in the domain of non-zero integers, let I, x, y be the predicate x over y is an integer. Translate the following into English, determine whether the statement is true or false, and explain why. So here, I'm going to translate these into like formal English, like just writing it out how, you know, the really robotic sounding for all integers x there exists in it, you know, anyway. So for all, so we're in the domain of non-zero integers. So for all non-zero integers y, there exists a non-zero integer x. So whenever you introduce a new variable, you have to state the domain over again. So that's why it's for all non-zero integers x, and we already had stated non-zero integers y. So for all non-zero integers y, there exists a non-zero integer x, such that is kind of just the thing you tack on before you write the predicate. X over y is an integer. So this means now the order, the thing that we're going to see in this exact problem is the order of the quantifiers matters. So what this is saying is it's saying for all integers y. So I'm going to give you an integer. I get to pick an integer that I want. So for that integer that I give you, can you find me one integer to spit back at me? Doesn't have to be the same, could be the same, such that when I take x divided by y, it's an integer. So for absolutely any integer I give you, could you then spit me out one that would produce an integer when we took their fraction? This is true. And it's specifically because I give you the integer and then give you a second to spit me another one back. Because essentially, for example, there's a bunch of examples that could make this work. But if you just spit me out the exact same integer, then it's just going to reduce to 1. Because let me take it one step further. You gave me the same integer, so it just reduced to 1. So no matter what integer I give you, you can give me another integer such that when I take x divided by y, it's an integer. Another example would be if x equals 2y. So it would end up being 2y over y equals 2. So essentially, if you gave me any multiple of the thing I gave you, it would work. Does that make sense? Needs to charge. Okay. I actually need to charge my laptop. Let me plug that in real quick. So the next one, pretty much the only thing that's different is the order of these quantifiers. So if I write this one out in English, we've got there exists a non-zero integer x such that for all y, no, be careful, for all non-zero integers y, we're introducing a new variable, so we need to state the domain again. X over y is an integer. So I moved the position of the such that. Essentially, the such that usually is always placed after there exists, because there needs to exist a thing such that something else is true. So there exists a non-zero integer. So I go off in the mountains and I find this integer, this holiest of integers, and I give it to you and you're not allowed to change it and I'm not allowed to change it. It is the integer of our life. So there is this one integer such that for every single other integer, x divided by y is an integer. Is that true or false? It is false. Very, very, very false. There is no singular integer that is divisible by every other integer, essentially. That's the reason. So false. There is no one, what? One, well, this is implying there could be more than one, but there's not even one. There is no one integer that is divisible by all other integers. And I say divisible because we're taking the x divided by y, so there's no x value such that I can divide it by y and actually get an integer out. So for instance, if y equals 2x, then x divided by y would be x divided by 2x would be 1/2. That's one example of the many ways you could show that that wouldn't work. So there's no one integer that is divisible by absolutely everything else. So like the order of those existentials is essentially what mattered here. Yeah. How far? Like this far? Because there's none written down in there really. Oh, down. Yeah. Oh, do you have the little bar on Teams in your way? I know there's a way to get rid of that. I feel like if you just like hold your thing over it for a little while and then make it go, I don't know. It's not on mine. But anyway, I can scroll down a little farther. There we go. So yeah, the difference between these two is that in the first one, I chose the integer, but then you got to find the one integer that worked for that. So like I gave you something, then you spit me back something else. And no matter what I gave you, you could go and then find the one that would work. Whereas in this one, we start with something that is set and you cannot change it, and it has to work for every single other thing. And that wouldn't work in this case. Questions, concerns on this question? 32. All right, well, we're just gonna keep chugging. All right, I'll wait like 5 more seconds in case people are still writing something down. Or realize they have questions. And 1 moment. Okay. Sorry about that. So the next thing we're going to want to do is we want to be able to negate quantifiers. On the quiz. On the quiz, do you need to show true, false? I assume you mean for something like what we just did. It depends on the question that I wanted to ask you. Let me think. For this quiz that's coming up, so this quiz that's coming up, and I'll write this out in chat at the end of class so you have it. Oh, my English broke. This quiz coming up will definitely have propositional logic on it. It will have a question like the one where you have to fill in the steps, maybe even 2 questions like that. So there will be 1 or 2 like that. And then let's see, what do I want to put on from 1-3? I haven't actually decided yet. From 1-3, what I would probably do for this quiz is I would probably just ask. So I would do one of 2 things. I haven't written the quiz yet, so I don't know what I'm going to feel like doing. But I won't do something that if I don't tell it to you right now, then it won't be on it. I will not do that to you. It will either be a true false like this. So like one of the quote unquote more simpler ones where it's just this kind of single predicate. So I could ask you a true false in terms of a predicate, but it would be one like those. And then the other thing I could potentially ask you is to translate, but I wouldn't ask you for the true false of the translation. I would just ask you to translate. So something like this, all bears are fuzzy. Or something like this, I could ask you to translate something like this. And what I wrote down here in this kind of formal would be perfectly fine. I would not ask you to do a true false on that type of thing on this quiz. Might show up on the exam, but on the quiz for Thursday, those will be the things. All right. We want to negate quantifiers. Now the thing is, this is where these rules are going to come back up a little bit. Because when we negate these things with quantifiers, we have to do them in kind of full, and I'll talk about what I mean by that in a second. Whereas it's not, so we have these 2 new rules that we're going to write down in a second. And they're kind of going to get added into these 2, these ones. Now my explaining is going off the rails. These 2 new rules that we have are going to get tacked into the rules that we already have, so you will have them on an exam. That's kind of what I meant. They will be tacked on to the rule set. These 2 new rules will only be used when we're negating quantifiers, whereas all the other ones are used in a vast majority of ways. But we will kind of need to use De Morgan's particularly De Morgan's and implication are the 2 that are going to come back to bite us in this type of thing. And we'll see that in a second. Anyway, so we've got the first one when we want to negate a universal quantifier. So we want to negate something that has a for all. You're essentially going to switch it to a there exists, and the negation essentially comes inside of the quantifier. This is going to be called universal negation. So when you ever need to say that's the rule that was used on that step, it's called universal negation. And then the other one, if we start with an existential and we want to negate that, this will be called existential negation. Oh Lord, existential negation. And it's a very similar idea, is the negation comes inside of the quantifier and the quantifier now changes to a universal. So these are kind of nice because they follow the same pattern. So essentially we bring the negation inside and then we essentially switch the quantifier. So we bring the negation inside and switch the quantifier. Now, when we're doing something like this, the instructions will say something like simplify until no quantifier and no connective lies within the scope of a negation, which is big, scary words for essentially what we won't want is, do I say this in the, nope. So we don't want things where the negation is still outside of a nexus in front of a quantifier. You know, the fact that this is in the front is bad, which is why we have these new rules. But the other thing is that we also don't want things, now I'm just pulling these off the top of my head. They can be for all, they can be exist, it doesn't matter. Nope, that doesn't get a parenthesis. If we were to bring it inside and then we had something like this in the back, because this negation is in the scope, is in front of this whole big statement, we would actually then need to put that negation through using De Morgan's, which is why De Morgan's is going to come up and bite us in the butt a lot now. So we essentially have to push that negation through until all we have, so essentially we need just like not P of X or, you know, whatever else, not Q of X, not Q of Y, whatever. So it can't be attached to any logical connective. It can't be attached in the front of a logical connective. Or, so let me actually write this down. You could end up being not P of X or Q of X. That's fine because the not is just attached to the P of X and not in front of the entire or statement. So when the instructions say simplify until no quantifier, no connective lies within the scope of negation, it just means you need to push the negation through all the way so that the negation is only in front of a single statement. It's not connected to an and or an or statement in this type of way. So we should have time to do one of these. And then we'll probably call it a day, even if we're not quite at the end, because the question after that is very long. So in example 2, we looked at two statements. We looked at for all of x, P of x implies, sorry, I can't read. For all x, Q of x implies P of x. For all animals x, if x has wings, then x can fly. And then we looked at there exists Q of x and not P of x. There exists some animals that have wings that cannot fly. The second one is actually the negation of the first. And what we're going to do is we're going to prove that. And really, by prove that, we're just going to say we're going to negate the first thing and realize that it turns out to be the second thing. So with these negations, these actually take the form of like a proof because we do them in steps. I might need to move that line over, give myself enough space. So we essentially want to negate the for all statement. So essentially the given is not the thing we want to negate. So we're going to have not for all x, Q of x implies P of x. This is our given. And so these are always going to start with one of our two new rules, universal negation or existential negation. Since this is a universal statement, we're going to start with universal negation. So let me write the universal negation. So we bring the negation inside the quantifier and switch the quantifier. That looks really gross. That doesn't look like a good for there exists symbol. There we go. And the rest will stay the same so far because we're just bringing it inside. And then again, with the fact that simplify until no quantifier, no connective lies within the scope of a negation, this negation is in front of a statement that has a logical connective in it, has the implies. That's not good. We need to push it through. We don't have a rule that tells us how to push a negation through. Can I make this a bit bigger? Come on, maximize. We don't have a rule that tells us how to push through a negation into an implies. No rule on there tells us how to do that. So what we need to do first is we need to change the implies to something else using the implication rule. So actually, let me bring that. Can I now make this? Oh man. And now I got it. There we go. So the next thing we need to do, because we can't push that negation through until we have something that's not an implies, is we need to use the implication rule to turn this into not Q of X or P of X. And this would be by implication. Oh, I haven't been putting the lines that we use it on, so that was on line 1 and this was on line 2. And now that it's no longer an implies, we have a rule that tells us how to push through the negation. We have De Morgan's law. So now we push that negation through using De Morgan's law. So both of the things turn into nots, and then our sign in the middle flips. And then the last bit is we just need to clean it up a little bit. The only thing we're going to clean up is the fact that we have a not. If you ever have a not, you want to get rid of that not. So the very last thing we'll do is we'll use a double negation rule to get rid of that not and just turn it into Q of X. So this is by double negation on line 4. So this one, that's where we would stop. We'll see one next time where when you're going the other way, so if we started with a there exists, you would end up in a place where you had an or statement. You would always want to change it back to an implies. So remember how I said that, the there exists connect to the and the for all connects to the implies? That also means that we always want to state them together. So if we were negating an existential and we came out to an or statement, we would want to use the implication rule to turn it back into an implies, because we always want our final thing to kind of have their matching symbol. So if it ends in a for all, we need it to change into an implies. Here, we didn't really need to do anything more because it's already an and that's what the existential needs. But we'll see that next time. One note about these types of questions. Whoops. So these types of questions will not be on your quiz. Let me just phrase that right now. But when it comes to doing these types of questions, yes, they take the form of a proof table, which I've said you will not do from scratch. But I meant that about formal proof tables. It is possible that I will ask you to formally negate something from scratch. Now, the reason that there's a difference, and I don't feel like a terrible person doing that, is that these negations actually follow a very similar pattern. You always start with the negation rule. If you started with a for all, you're going to use implies. If not, you're going straight to De Morgan's and then using implication. So essentially, these ones, it's always the negation rule and then a combination of implication and De Morgan's in some fashion. Like it always follows the same kind of pattern, where the ones from 1.2, I can kind of give you whatever the heck I want, and it doesn't really have any type of pattern to it. So these ones, even though they take the format of the things I told you that you wouldn't do from scratch, these particular types of things, these negations, are fair game for scratchness. Hopefully that made sense. To be done from scratch because of the pattern that they follow. Just want to be super clear on that so that someone doesn't get surprised by that later. So regular old proof tables, if I just say prove this statement, you will not have to do those from scratch, but these negation things is fair game to be done from scratch. Anyway, I know I kind of already talked about your quiz, but I'm going to type it down in chat in case you need to find it later. So your quiz on Thursday will consist of proof tables, and those will be fill in the blank. And then what was the other thing I said? True, false with, I'll say simple predicates. And I'll say like the beginning of 1.3 notes. And then also possibly translating predicate statements with or without quantifiers. So I could ask you to translate something that has a quantifier. I could ask you something to translate something without a quantifier. Actually, translating without a quantifier isn't interesting. So it'll probably have a quantifier on it, but I already typed it out. Anyway, I feel like there was one more thing I wanted to say. Oh, let me try to say this before I forget. So in terms of your quiz on Thursday, pop back over here. Your proof table will be like this, where you just have to fill out the reasons. When we get further to the exam, and I do always give you a study guide and like some practice problems for the exam. On the exam, sometimes I give you the proof table, but the thing that I don't give you is the statement, and I actually give you the reason, and you then have to give me the symbols that go there. So like I give you the reason, and you actually have to give me the statement. So there will be coming up some questions where you have to kind of do both. You not only have to tell me the reasons, but sometimes you'll actually have to give me the statement. On the quiz coming up on Thursday, it will be exactly like this, where all you have to do is fill out the reasons and the steps. To clarify, these little numbers are technically called the steps, because I think that's how I laid out part of your quiz that I've already started. But we will also be doing some warm-ups on Thursday with questions similar to what you'll see on your quiz like we did last time. Anyway, I think that's it. I'm going to stop talking now. If you have questions, feel free to stick around a little bit. Otherwise, we're done. Have a good day. I will see you on Thursday. And, oh, we technically have 5 more minutes. I thought it ended at 12:50. I forgot. Anyway, well, the next question's too long to start. It's not worth it. So be free 5 minutes early. If you have questions, let me know. Otherwise, I'll see you on Thursday. How do you justify? Let me